of notes before we get started with anything else. First of all, you do have an iMath AS assignment due tonight. You have some due next week and the following week. So there's lots of Monday Math AS stuff that's due. So make sure you keep on top of that. I will have the next assignment posted when it's due, like in your assignments. But if you went in to do the stuff that's due tonight, you'll see that there are a few more assignments listed there that just have due dates farther into the future. But they are all on Mondays. Let's see, aside from Math AS stuff, oh, I know. Derivative mastery test. I will alter your syllabus to reflect this, but we decided on Friday last week, rather than having it on Monday, October 29th, it's going to be, well, it started on Wednesday, October 31st, so that'll be some part of it in class that time and part in your recitations. I'll put the details in an announcement and change the official date that's listed in your syllabus from Monday to Wednesday. But in any case, just kind of where we're going over the next few weeks, couple weeks until then, and then on through the rest of November. So we've got a derivative mastery exam that's coming up the end of this month, and test 3, which is coming up at the end of, towards the end of November. It's during that last week of classes. So they aren't completely separate from one another. The test 3 covers everything from after test 2 through the end of the semester, other than just, obviously you still have to know what constant rate of change means. But these two kind of learn about derivatives. That's kind of like the calculational aspect of it is kind of interspersed with other things. So I just don't want you to think that this is all derivative stuff and that's going to be on the derivative mastery test, and then after that, that's what's going to be on test 3. Test 3 is more about all the, like the theory, the build-up, this kind of stuff that you're doing on this quiz. How do I formulate rate of change functions? And a lot of the other things we're going to do once we're good at finding them. But as a part of this first half of this next module, we're going to be doing a lot of, well, we actually have to do these calculations, get these closed form rate of change functions. So what I want to talk about today is mostly about the notation for that and some extra relationships, kind of re-emphasizing things that we talked about at the end of Module 2, before Exam 2, about exact rate of change or exact accumulation modeled by integral expressions, open form. We're going to kind of go back and forth between that exact accumulation expressing a rate function, and then now that we can express some rate functions exactly, how we can write things in multiple ways, open form, closed form expressions. So we're going to talk about that today, maybe a little bit into more shortcut rules for derivatives, but Wednesday and Friday will all be about those sorts of things. So let's see. Notation, first of all, because we've just kind of talked about one notation so far, and we will be using that. But if f is any function, whether you think of it as an accumulation or you just saw it was listed f of x equals, f of q equals, whatever it might be, if x is what we're using as the placeholder for the independent variable, r sub f of x is what we're going to use for its rate of change function. That's one of multiple notations we can use, but this is what we've used so far. But this is used to indicate f's rate of change function. This is just exactly how we used this in the previous unit when we were talking about starting from a rate of change function and working towards figuring out what was a rate of change for. So this expression that we're working with is the second method, r sub f of x equals f of x plus h minus f of x over h. That's that method 2 that we talked about. And again, the benefit of this method 2 over one that more directly modeled our other way around process, working from rate to accumulation, the benefit of this is that it gives us a rate of change function that is all connected instead of being a sequence of steps. The steps occurred when we had rates that changed abruptly that matched a piecewise linear accumulation that was one chunk at a time, and we kept one rate of change for an interval of length delta x. This one doesn't keep one rate of change for any length of time. It's calculated using an interval of width h, and then the moment that x moves even the tiniest bit, we have a slightly different interval to use, but it's always with h. So horizontal distance of h, that's why h is used. So in any case, this function here is going to be what we use for our standard definition because it does create the types of functions that we're used to seeing and not having to write as a piecewise expression. the types of functions like polynomials and exponential functions and logarithmic things where everything, not everything, but they're connected over long swaths of their domains. So the only thing is that we can use this notation a couple of different ways, and we've talked about this, and we've actually used it a couple of different ways. We can use it to mean an exact rate of change function, or we can use it to mean an approximate rate of change function. And the difference between those is just based on the parameter value for h that we're thinking about. So if you're doing some computations manually, like you did on your quiz, where you're asked to calculate the approximate rate by looking at this graph and finding some intervals, you need to have an h that isn't microscopic. So we had relatively large, even if the numbers were smaller, relatively large values of h, or intervals where we could see the distance between the left and the right. And in that case, what we're getting is an approximate rate of change function. And I can imagine that as that h, that horizontal distance, the change in the independent variable, gets smaller and smaller between the 2 points whose rate of change, or whose difference we're using to model that rate of change, the dy's and the dx's. As that h value gets smaller and smaller, we can see that for this sort of setup where we have these intervals, as long as we're within a section of a function f where it doesn't have any gaps, like asymptotes or something strange, then as h gets smaller and smaller, we get, over the domain of the function f that we're looking at, we get something that kind of centers in on one particular shape graphically, or something that we can imagine by doing some algebra like we did at the end of class on Friday. We just did a couple of polynomials, an x squared polynomial for f and an x cubed polynomial for function f, a square area, and there's x cubed with some coefficients in it for volumes of a sphere. But in any case, this r sub f of x, it can be used for approximate or exact depending on what we're thinking of h as representing, something extremely small or just any old number so that we can do some computations. So I want to talk about, like I said, kind of the back and forth between what we were doing earlier in the semester and what we're doing now, and the use of integral expressions to notate accumulation, as well as, well, we saw on Friday we can find closed form expressions for rate. We should be able to do open form expressions for accumulation and closed form. So on Friday we talked about, if I had the function for the area of a square, f of x equals x squared, we came up with the rate of change of f. R sub f of x was 2x. We did that f of x plus h minus f of x over h. We did some general algebra sorts of things, expanding a binomial and factoring out a common factor to reduce. And so if I have an accumulation, the function rule is x squared, and I have a rate of change that's 2x, we talked about the relationship between those before test 2 in terms of writing accumulation using an integral symbol. So I could write f as an accumulation due to that rate 2x. So here's something that we talked about how to write before your last test. So if 2x is the function rule for the rate of change of function f, r sub f of x, if I integrate that, I get an exact accumulation. And I can express this integration between 0 and x. If you think about, that's what we saw in the graph. We started at a value of 0 for the independent variable and went onward because it was modeling a square. But if I integrate or measure the accumulation due to rate 2t, so our mdx sort of expression, 2t times dt, we let t vary from 0 to x, I get a function that is a function of x, and I'll call this f because that's what it was. This is the rate of change of function f. If I measure the accumulation due to f's rate of change, I get f back when I'm done. Now, this is actually a special case here because I don't have quite all the parts that we normally do for total accumulation. This is like a net accumulation between 0 and x. But if you think about a square, think about net accumulation from side length 0 to side length x. How much accumulation of area, or what is the area if x side length is 0? If I have a square whose side length is 0, how much area do I have? 0, nothing, right? Nothing's accumulated yet. If I'm at side length 0, there's no area. So this is actually a special case of what we talked about for total accumulation also. This is just, there's no area at x equals 0. I could say in general that f of x equals x squared, this square accumulation of area formula, is equivalent to a squared plus this integral from a to x of the rate function. No, it's a. A is wherever we start accumulation. If I start accumulation at 0, that's area of the square when side length is 0, plus the accumulation onward from that. Or if I started this with, if I wanted to express this in terms of, well, what's the area when the side of a square length is 1? Right, well, that'd be 1 squared plus the accumulation from 1 onward. Now, it doesn't say this in here. I really wouldn't want to use, in terms of thinking of this as something to do with the square, values of a that are negative. That wouldn't make any sense in that context. But if it meant something else, the accumulation should still work. I have a y initial plus my sum of all my mdx's. So if I have an initial value, whether it's 0 or something else, just that f of x is x squared, we actually know the closed form function here. So I can find this initial value, f of a, by just plugging in any value a that I want into f of x equals x squared. That's something that we didn't have last time around. When we were working on this before chapter 2, we had the rate function, or maybe just a name for the rate function, but we didn't have any function rules written out in closed form for accumulation. So this is something new that we can do. Meaning, if I integrate a rate function, I get back the accumulation. So I took an accumulation. On Friday, we figured out the rate function. And if I integrate that rate function, I can get back to accumulation. So we kind of went back and forth, but in a certain sense, it's not necessarily back and forth. We can just write it in this other form. So this doesn't look like the accumulation that we started with, x squared, but this is equivalent to x squared for any value of a. For any value of a, this open form expression here tells us the same as f of x equals x squared. So I can say f of x equals this. I can write it in this generic form, and this generic form here would be true for any function f of x, right? This is the specific one for this f of x equals x squared, a squared plus the integral of the rate function we determined last Friday. Well, it was 2x when we did it, but we change our variables so that we can have a integral function of x. So we use a dummy variable, let t vary between a and x. So let's think about this with our sphere. We figured out, last thing we done on Friday, was that if I have volume of a sphere with radius x, it's given by 4/3 pi x cubed, and the rate of change of the volume of that sphere was r sub v of x, I guess, equals 4 pi x squared. So see if you can write an integral expression that's a way to write v of x in open form. So if you can write v of x equals and then something with an integral expression, that would mean the same thing written in a different way. So I want to write something like v of x equals, and then something involving an integral. And there are infinitely many things that you could write here that are correct, by the way. There's also infinitely many wrong things, but you at least got a good shot. There's infinitely many of them. If you wrote one really fast, see if you can write a second one. Or in general, what all these infinitely many correct answers might look like. one thing. What's going to be part of the integrand here? What part would I need? What thing would I need to integrate in order to have this have a hope of being related to v of x? Yeah, there's 4 pi something. So if I write 4 pi, I don't want to use x here, right? I'm going to use 4 pi times some other letter. I'll use t. What else do I need in the integrand besides that rate function rule? Yeah, dt. I need my m and my dx. So here's my m dx sort of expression. The rate and the amount of time that I use that rate for, where t takes on all the values between, here's where you have options. Yeah, I can use a and x, and if I have that, what else do I need here besides that? Yeah, v of a, which I could also write, instead of writing the symbol v of a, since I have a function in closed form here for v of x, I could write 4/3 pi times a squared, or a cubed rather, sorry, and then plus this, integral a to x of 4 pi t squared dt, or pick your favorite non-x variable for that. So this would be v of x, or I could even write, let's see, 4/3 pi x cubed equals this. I could make it look like an equation instead of a function. This would be a true numerical, well, semi-numerical expression. Doesn't have a function name in it. It has all variables and an integral sign. You don't have to use the general symbol a. If you wanted to use 0, like we did for the square, we could do that. In terms of something I could write that involves starting at 0 like we did for a sphere. So in that context, that would be an easy starting point. I could think of this v of x as being v of 0, which is 0, plus an integral from 0 to x of 4 pi t squared dt. And that would obviously be the same as just, since this is equal to 0, when x is 0, v of x is 0, or v of 0 is 0. So we could write this, 4 pi t squared dt, from 0 to x, and call that v of x. There's a lot of different things we can say, but the point of all of this is there's this interrelationship between finding a rate of change and finding an accumulation. You can get one from the other and the other from the first, and you can express them. We found out how to express a couple of functions, rates of change functions in closed form. We're going to focus on being able to do that for any function soon. But if I have a rate of change, I know how to express accumulation in open form. That's from last unit, from chapter 5 material. So just make sure you don't forget about that aspect of it, because this will help us solve some additional issues. So for instance, if you remember the questions with the race car, and I asked you to figure out, like, how far did the race car move between time, like, 3 and time 7, and we had a position function. It's like, oh, well, how far did something move between time 3 and time 7? Let me do this in terms of volume here. How much does the volume grow? Because we know it's going to grow if I increase the radius. Volume increase between having a radius of 3 and a radius of 7. Let's say x is in inches. Just some sort of unit, so it means something. So we could write that 2 different ways. One in, well, maybe 3 different ways. One with function notation, one using the accumulation function rule, and one using open form integral of a rate function. So how much does the volume increase between x equals 3 and x equals 7? Oh, I could just look at this and say, oh, it would be whatever final minus initial, v of 7 minus v of 3, right? That would be one way I could say it. If I wanted to actually use this function rule, since we have it, we could say 4/3 pi times 7 cubed, and or minus 4/3 pi times 3 cubed. You could factor that if you wanted to. I was going to do that, but I won't. It'd just be confusing. 3 cubed. Or if you want to use the accumulation open form, how much does the volume change between a radius of 3 and a radius of 7? Accumulation occurring between 3 and 7 due to the rate function 4 pi x squared. I can use x, I could use t. It doesn't really matter what letter I use in this case because I'm not trying to make a function, just an expression for a number. But 4 pi, I'll just use t. You don't have to use x in order to do this, but in any case, each one of these 3 represents a numerical value. The first one, just using function notation, you'd have to know function v's rule in order to get it. If you know function v's rule, you can write number 2. And we can also write number 3. And GC can calculate any single one of these and will give us the same result. For part A, you'd have to have function v defined separately. But any of these 3 tell us accumulation between 2 values, final minus initial. And keep in mind that integral version of this, the accumulation or the change in the accumulation, this net change between radius 3 and radius 7 due to this rate. On your last test, there's a question like, let's see, what's the net change in position of the race car between time 4 and time 17 or something like that? And like, oh, we integrate the speed function, how fast the little race car was moving, between the 2 points in time to figure out the net change in position. We don't have to know the position function. We can integrate the rate of change function to get the same thing. All right, so let me have this written out in symbols here. So we could write that, v of x, or its rule, equals the accumulation from 0 to x, because this was in the context of a sphere starting at 0. Or in general, you could write this as 4/3 pi times whatever cubed, a cubed in this case, plus what happens beyond a, the integral from a to x of that rate of change function. So this is called the fundamental theorem of calculus, all the stuff that we're doing. And that's why it's kind of our goal for the whole year, is to go back and forth between rates and accumulations. Unlike, fundamental theorem of algebra, if you remember that was the rule that you probably talked about. It's like equations have solutions, generally. Great. There's a lot more details to it than that, but it didn't form your whole source of how you do everything during the class so much as this does. But exact or total accumulation function. If I have that, whether it's I call it an amount or an accumulation total amount, and even if it's a net amount, whatever it might be, if I have some sort of accumulation function or how much of something there is, you can think volumes or areas, you can think about distance traveled or whatever you want. If it's net or total amount of something or accumulation of something, I can find rate of change functions using this method that we were talking about last week and a little bit the week before. R sub f of x plus h, or r sub f of x is f of x plus h minus f of x over h. This is our dy over dx computation. And for it to be exact, we let h be essentially 0. We can't have it equal 0 because that doesn't make any sense, but you can imagine what happens as h gets closer and closer to 0, as we saw and will continue to see. Certain pieces of our computations also become essentially 0, and we can see what's left over. So if I have an exact total amount, total accumulation, or even net accumulation to start with, I can find the rate of change of that and express it using this method. And even if I don't go through any algebra to write that in a niftier, more usable form, I can model this capital A sub f, our net accumulation from last chapter, last unit, by integrating that. I can find my net accumulation starting at any value of a that I want by integrating from a through x. So this tells us net accumulation from specified point onward. Or if I wanted, I could find the total accumulation. So if that was something else, if this f of x wasn't just a net accumulation, I already would have recovered that by this point. But I can talk about an exact amount or total accumulation by just adding on one additional term, that y initial. So y initial plus all of our mdx's instead of just, ooh, sorry about that, hit the trackpad. So have our y initial plus mdx's instead of just the net accumulation, which is just the sum of all of the rates times small bits of change. So fundamental theorem of calculus is usually presented in other textbooks in two parts, but they're really saying the same thing. It's just this interrelationship between rate functions and accumulation due to those rate functions. And whichever one you start with, there will be different notations for this, but you can get to the other from that. You can express numerical amounts of change, or you can express net change as a function if you know the rate. And if you know the accumulation, you can find rates using this setup to express change over small increments, generally in terms of location x. So just to restate this again, this was at the bottom before. So for total accumulation function or total amount function f, the rate of change that's associated with it, r sub f, and any value a that's in the domain. So we haven't really specified, when we're talking about these, I'm not going to like pick weird functions like square root functions and then talk about negative inputs to the square root. But just as long as we're picking reasonable values here, if I have an a that's in the domain of the original function f and its rate of change function, then I can express f, this total accumulation, by taking any initial value of the function plus integrating thereon out. So from a to x, as long as I stop someplace that's in its domain, or imagine this only going through certain parts of the domain if that's an issue. Polynomials, don't have to worry about that. That's why we start with them. Thinking about, remember that net change we were talking about? Had that like v of 7 minus v of 3 that we just wrote down? You could also think of that as just being a rearrangement of that first line there. So to find total accumulation, you have a starting point plus the change past that. You can also model change over a specified interval, any specified interval, by subtraction, right? So this f of x minus f of a should be the same as an integral between a and x, just the same way as the change between v of 7 and v of 3, final minus initial, is the integral between 3 and 7. Same sort of thing. It doesn't have to be all numbers in that expression. It can be symbols like a's and x's representing either a parameter. We were using a as a parameter or starting point, and x actually as our independent variable of a function. But so I could express this with this form here. Or I could also use any particular numbers. I'll say a and b. So a is a starting point and b is an ending point. And typically when you see, if you've taken a calculus class before where you talked about this, or you looked up fundamental theorem of calculus because you saw it someplace, typically you'll see it written as two parts. One that looks kind of like the first bullet point up there, f of x is an initial value plus accumulation due to an integral. And then a second part that is written as the last bit here, f of b minus f of a is an integral. Well, it's not necessarily the exact same notation, but subtracting two function values is the same as integrating that function's rate of change between the same two independent variable values. So, but all this is just a rearrangement of, they're all just rearrangements of one another. So you can think of it as integrate a rate of change between two numbers and get a numerical net change, or thinking about just rearranging the equation to a different form, expressing a function based on its rate of change plus an initial value. So in any case, just a different way to think about this. But you've seen some parts of this that are more closely related to how we talked about it last chapter, just integrating from a to x in your homework that's due tonight, if you started on that. But just to kind of reiterate that and go a little bit farther, we're going to be using this repeatedly, this fundamental theorem of calculus. This is another thing that's going to be on your test 3. Your derivative mastery test is not about theory of how stuff works and do a bunch of algebra. It's just about memorize a bunch of rules and make sure you know them. It's like I'm testing on your multiplication tables. I'll give you more details about how the exam is going to work specifically in an announcement and post it in your homework tonight. But that's just a straightforward, not like our other tests, memorize a bunch of stuff, and it's actually handwritten, not multiple choice. Test 3 covers all of this sort of stuff that we've been talking about, the theory behind this, why this works the way it does, how we developed our rate functions, how we express accumulation in general, how we can go back and forth between accumulation and rate, and some other applications topics that we'll get to in November. So I already said that. Expresses net accumulated change from A to B. So far, we've talked about this volume of a sphere example, and we found its rate of change. So we also know, just kind of recapping this after that the volume in general can be expressed by any initial starting volume for any given radius, or if it's out of context of a sphere, you can pick any number you want for A. Polynomials are perfectly fine with negatives. Plus the accumulation between A and a general value of x to express a function v of x. Or, for example, I use 7 and 2 here instead of 7 and 3, but the change in the volume, net change in volume between a radius of 2 and a radius of 7 would be expressed by this. And you could use t's or x's or whatever letter you want. There's no restrictions in this last integral here because it's not a function where I want it to be a function whose independent variable turns out to be x. It's just a numerical computation. So we've used up our square and sphere. Let's look at a different function. Get some other examples in here and do one more different type of algebra stuff for the day. So let's say I have this function g, and I'll give you its rule in a moment here. But if it goes through these 2 points, 1, 4 and 4, 2, those 2 correspondence points, if I want to estimate the rate of change by using that relatively long interval given, what would the rate of change for the constant rate of change for this purplish line segment be? dy over dx would be, well, change in y, and decreased by 2, and x increased by 3. So that's negative 2 over 3 as its rate of change. Now, that's not a particularly great estimation, especially zoomed in this far. Like if you zoomed out farther, that'd look perfectly great. But zoomed in this far to this level of closeness, we can see that that's not a great estimation. So if I wanted to know more about what's the rate of change near x equals 1, which I can go forward from 1 by however many units I want to do that, if we're going to use our sliding interval method as opposed to having preset locations of interval boundaries, I say, well, let's go forward from 1. By 3 whole units, I get this r sub g approximate version is negative 2/3, negative 0.6 repeating, or here's rounded off to a few decimal places. If I want to know a better estimate at what's going on at 1, I need to pick a smaller interval that includes 1, or is nearby to 1. So if I look in closer, let's say I pick one that's 5/1000ths of a unit away, or 5/100ths rather. Here's our function here. So you can play along if you want to plug in 1.05. You should get this 3.934 approximately, again, rounded off. But this function we were looking at was the rational function g of x equals 12 over x plus 2. So from a very large value of h, not essentially 0, we got an approximate rate of change of negative 2/3. If we use these 2 much closer points, and even if I tried to draw on here a straight line segment between those 2 points, it'd pretty much run into that black line. So it should be a lot closer to what's actually going on right around 1. And I can make this smaller and smaller and smaller and smaller, but just this level of, I zoomed in quite a bit here. If I just use these 2 points, I can see that there's a small amount of change in y, a small amount of change in x, and we should be able to compute the ratio of those changes to find the rate of change. And usually we can apply that to anything in this area here. But if I say, okay, we'll use that rate of change at x equals 1, the way that we have. So to find a rate of change for x equals 1, we take a small interval just to the right of that, 1 through 1 plus h. and then we find the slope. So if we do that, oh, sorry about that. I just clicked on something. There we go. I should get still a negative value for sure, but much more negative than when we use the 3-unit long or 3-unit horizontally purple line segment. So these are both estimates. Neither one is exact per se. This one's pretty close though, because I've used a very small interval. What I'd want to do in order to find an exact value of this rate of change is to come up with an exact rate of change function and then use that function. Because by plugging in numbers repeatedly, all I can do is kind of see a trend, and it may be not a very nice number, like weird decimals. I'm like, I don't know what function is leading to this weird looking decimal. So negative 1.311, that's not something that looks like, oh yeah, that's 1 2/3 or something, negative. So rather than just kind of guessing what an exact value might be, we could see maybe a couple of things like, well, using this interval as opposed to the short one as opposed to the purple one, I can see, well, that looks closer because right around 1, right around x equals 1, the graph is going more sharply downward than it was by the time we got to 4. When we have these intervals, what we're getting is an average rate of change over that interval. The straight line, the constant rate of change that would produce the same amount of change overall over that interval. And so the graph was going down sharply and then kinds of flattens out. It's that rational function, horizontal asymptote pattern. So this purple line is much less steep than the black curve is right around x equals 1. This blue little tiny line segment that I put in is much closer, but still it's between these 2 points where I know the graph is getting less steep as I go. So I know that probably my actual rate is slightly more negative than this. I don't know how much more, but we can figure it out. But as I said, in order to figure it out, we can't just look at numerical values and necessarily figure out what an exact rate is going to be. What we need to do is construct an approximate rate function and then imagine that h getting smaller so that we can see what happens algebraically for any value of x. If there's something that I can reduce and say, oh, well, this is going to turn into 0 and that's going to turn into 0 as h gets incredibly small, and I have something usable left, then that means I have a function rule that I can use for this exact rate of change function. So just keep in mind, though, through all of this, we're doing a lot of algebra and a lot of notation, a lot of everything else. Don't forget about the actual meaning of this rate of change, and I kind of said part of this a second ago. But if I have a rate of change at 1, that's this negative 1.311, back to what we were talking about at the end of August. If I have a rate of change between two quantities, it means for a change in one of them, the change in the other is that rate times as much. So we're talking about things that don't have a constant rate of change everywhere, but we use this as a constant rate of change over small intervals. So I can imagine if x is near 1, if I change x by a small amount, the y value, the dependent variable, would change by 1.311 times as much in the opposite direction, the negative part of that. So for a small change in x near x equals 1, y will change by about negative 1.311 times as much. So that's talking about how we use our rates of change. This can help us predict future values after small amounts of change, y initial plus m dx. So let's look at the algebra of this. This will be our last thing for today. Suppose I want to find a rate of change function for this g of x, which was 12 over x plus 2. Using our trusty model, in this case I'll call it g of x plus h, since it's function g instead of function f, g of x plus h minus g of x, all over h, change in y over change in x, and then we imagine h becoming essentially 0 so that we can get an exact expression, but we'll worry about that last. Let's first think about what would g of x plus h look like? What would the function rule g of x, or the expression for g of x plus h look like? Well, if it was g of 7, you put a 7 where the x is. If it was g of 19, you put a 19 where the x is. If it's g of x plus h, you put an x plus h where that x is. So we're going to have another rational expression just with x plus h plus 2 as the denominator. So here's a very messy looking expression for our exact rate of change function if we imagine h becomes 0. So let's do a little bit of algebra in order to make this nicer. So when we dealt with both our x squared, our square area, and our 4/3 pi x cubed, our sphere volume, we had a polynomial expression that we needed to expand in order to, that was the algebra we had ended up doing, expanding a binomial in order to simplify. There is no binomials to simplify here, but if you look at the numerator, that looks like some sort of horrible problem that you had to do in a college algebra class or algebra 2 class probably at some point in time. Subtraction of fractions with variables in them. So I can simplify this whole expression by looking at the numerator first and actually doing the subtraction. In order to subtract rational expressions like that, what do I need? Common denominator. Yeah, so we've got to get common denominators, which those are just different by a plus h. That doesn't tell us anything about what their factors are. Neither of them is factorable as a denominator. So it's just kind of like if I'm trying to subtract fifths and sevenths, I'm just going to multiply each fraction by the other's denominator, top and bottom. So kind of skipped over the step of writing it as two separate fractions here, but that's take that first fraction, multiply it by x plus 2 on the top and bottom. Take the second fraction, multiply it by x plus h plus 2 on the top and bottom. That makes both of their denominators this x plus h plus 2 times x plus 2, the product of the two earlier denominators. This numerator gets multiplied by the right one's denominator, and this one gets multiplied by the left denominator. They're both over the same denominator. We're subtracting. So this is a bit of algebra. I don't really want to review all the algebra. If that looks confusing, please ask. Email one of us later, look it up online, something. But once I've written this as a single expression in the numerator, as opposed to two separate fractions in the numerator, I can do a couple of different things. But one thing I can do right now, kind of similar to what we had before, in the numerator of the numerator, I've got some like terms that will subtract one another out. If you can see, there's this minus in the middle. I've got, if I distributed a 12x here minus a 12x there. All right, there's no 12x's in the numerator anymore. There's also a 12 times 2 and a minus 12 times 2 over there. Those are also going to be gone. So if you can see, the whole first half of the numerator, the numerator's numerator, is going to be gone. All that's going to remain out of that entire main numerator is minus 12 times h. So that the whole numerator of the numerator is negative 12 times h. And then it's over this common denominator. And then I've got the overall fractions denominator. Now, too many denominators and numerators. Fractions in a fraction. If you're dividing and you've got fractions or whatever, think about multiply by the reciprocal of the denominator. If you want to think of this instead of, I'm just going to write this by hand, instead of negative 12h over that two-term denominator, let's see, x plus h plus 2, or two-factor denominator rather, and x plus 2. Instead of writing that all over h, I can multiply by 1 over h. This fraction over h is the same, divided by h is the same as multiplying by 1 over h. And at this point, the best part about fractions, cross-canceling. There we go. So we've got this rate of change function, which I can write as then just negative 12 over these two factors, x plus h plus 2 and x plus 2. So at this point, the only additional algebra I could do would be to multiply out that denominator, but I can actually do this without multiplying out the denominator. There's no issues at this point with h being near 0. if you can see, there's not any divide by h anymore, or multiply by h, or both of those. If I imagine that this h is essentially 0, that means that the two factors in the denominator are essentially the same factor. Or I can imagine if h is approximately 0, this r sub g of x becomes approximately negative 12 over, well, x plus h plus 2 would be just about x plus 2. And the other thing is already an x plus 2. So I've essentially got x plus 2 twice as factors in the denominator. So here is our exact rate of change function for this g of x. It looks kind of similar to the original. We're going to talk about some more patterns with this. This is tomorrow's or Wednesday's task. But if you remember back to our r sub g, we were looking for r sub g of 1 on that graph. If I have this function, as opposed to just a graph to pick points and sub into, r sub g of 1 should be essentially negative 12 over, if x is 1, 3 squared. That's negative 12 ninths, which is negative, what is that, 1 and 3 ninths. Negative 1.3 repeating. Negative 4/3 if you want to reduce it. But in any case, if you remember, our results from doing this numerically, you had a negative 2/3, which was a poor approximation, and negative 1.311. That's pretty darn close to this. But without finding a rate of change function to use, we're not going to be able to get exact values by just looking at numbers that we assume are getting better. They're just going to be weirder and weirder decimals. But here's our kind of verification that, yeah, this makes sense. This matches up with what I was expecting. But it gives me a way to find not only for x equals 1, now I can reuse this rate of change function for anything on that rational function, 12 over x plus 2. What I'd like to do is be able to do it for any rational function of any sort and any sort of function in general overall. And that's where we're going starting next class. So I will see you then. Have a good rest of your Monday.